morning, Kishore sir. Kishore sir, good morning. Am I audible, sir? Hello. Kishore sir. Kishore sir, am I audible? Hello. Kishore sir. Participants, can anyone please respond?
Hello.
Yes, ma'am. Thank you. Kishore sir.
Yes, ma'am.
Yes, sir. Good morning, sir.
Morning. Yes, ma'am.
Yeah. Shall I start the session, sir?
Yes, ma'am.
Okay, sir. Just a minute. Any gathering comes alive when the right starts to it, and we have ensured the same to this FDP program. We, the team, here to bring the right amount of enthusiasm, knowledge, and practice to the gathering that obviously results success. By following all these mantras to our FDP 2021-22, very all day, to have now day of FDP 21-22. My name is S. Devi, Assistant Professor, Department of ECM, KLEF. And it's my privilege and pleasure to welcome dignitaries, professors, faculty, scholars, and students unitedly for today's session. I take my humble turn to introduce today's resource person. Dr. P.V.V. Kishore is a senior member IEEE, received the master's degree from the Cochin University of Science and Technology and PhD degree from Andhra University College of Engineering in 2013. He is currently a professor of image and video processing with the Department of Electronics and Communications Engineering, where he manages the image, speech, and signal processing research group. He is also the chair of the Biomechanics and Vision Analysis and Sign Language Machine Translation. He is an enthusiast in developing new innovations in the areas of computer vision and machine learning areas. He has authored several publications in these fields. His research interest includes how motion capture data models can effectively model low-end video objects in real time for better recognition and analysis. Once again, I welcome you, sir. In continuation with yesterday's session, I welcome you again on this platform of FDP 2021-22, sir. Kishore sir, now you are the presenter, sir. You can hand out the session.
Yeah, ma'am. Thank you, ma'am. Madam, is my screen visible?
Yes, sir.
Yeah.
It's visible.
Yeah. Thank you for the introduction, madams. And good morning, everybody. So let's build on what we have learned yesterday. So we'll show you some of the examples, basic though, but how to build a model in Python and TensorFlow, and on a GPU, how it works, and stuff like that. So first, just this one is a small example. I'm going to show you. Let me share. Let me run the program, because I'm not going to explain this, but I'm going to show you the power of deep learning. I think you can see me, right? So this is the model released by Google 3-4 months back, which was trained with more than 30,000 images of face, hand, and all other body parts. It can recognize all body parts, and it is quite good. You can just see me speaking. Are you able to see me? So this was built by Google. You can use it. It's called MediaPipe. So it's a very powerful human action recognition tool in 2-dimensional on video. So inferencing is quite fast. It's already trained model. You can just import the trained model and work on that. So this is the power of deep learning. So this is a very small code, because we don't do anything, and we just invoke the webcam. We use the MediaPipe API to build that, and then for what do you call the video capturing and stuff like that, we'll use OpenCV. So a very simple API to very simple code, like around 30 or 40 lines of code you can build, and you can use that. You can capture these things and work on that. So let's move on. So this is just a demo of what we can see. So let's start. Yesterday, one of our members asked how to train, what is training. So we'll look into the concepts of training and testing, and what are the things that are going to happen using, what are the things that you can, what are the applications you can build using machine learning algorithms or deep learning algorithms. So first, we'll focus mainly on CNN. That is what we have seen yesterday. So I'll try to limit my limit my programs only for CNN. So the basic here, you see the figure on your screen. So we have the requirements for a particular application, and we have the data, and we'll feed our requirements and data into a program or a model, and it will give the rules to match the data with the requirements. So that is what the training is. So data and requirements both are independent, and it will try to find a relationship between data and requirements, and that is the job of our model. And we'll get the rules to manipulate on the data in real time. So that is the idea of training. So the training process here is to find a relationship between data and the requirements of the application. And the output rules are in the form of a matrix, the training matrix or a trained program. And the rules are like a simple, in the rules out, will have a matrix with weight vectors, which are the relationship between our data and the requirements. So that is what the training is. Hope we all understood what training model infers. So let us start with what is the TensorFlow. TensorFlow is the API built by Google, maybe released in 2015, at the end of 2015. So it's an open source platform for building ML models. So it has everything. And let us see the architecture of the TensorFlow. The TensorFlow is the front end model, and it's built on all the deep learning APIs are in Keras. And it was developed by maybe around 25,000 engineers from all over the world. Even from there's so many engineers from TCS, Infosys, which are part of this. And you can see the basic, it has data sets, it has estimators like optimizers, the error finding models, and then it can be trained, the models can be trained on CPUs, GPUs, and the latest buzzword that we are hearing from last 1 year is TPU. The GPU architecture is basically designed for gaming purposes, but they are solving the deep learning applications also, but the more focused GPUs, so they call it tensor processing units. The architectures are built into the in a hardware format, so that the inferencing times will be very small. Our training times can be reduced, and then once you have all that, you can just save the model, and you can launch the model in cloud or on Android or in browser. For that, they have different TensorFlow based APIs, like TensorFlow Lite is for cloud platform, and under TensorFlow Lite, you can do it on Raspberry Pi, Android, or iOS, and then on browser also you can deploy your application.
Kishore,
Ma'am.
Kishore,
Yes, ma'am. Hello.
Kishore, sir, sorry to interrupt you, sir. Your voice is not clear, sir.
Yes, ma'am. Because
Sir, your voice is not clear, sir.
yes. I understood, madam. Same thing with your voice also, madam. Maybe our network is little, so it's not working properly, maybe.
Yes, sir. Actually, today, yes, sir. Today it seems to be slow. So your voice is coming in echo mode. Okay, sir. You please continue, sir. Please continue.
Let's see, madam. We'll wait for. We'll wait, or shall I continue? Or else shall I re-log in?
Yes, sir. You please continue.
Okay, ma'am. Thank you.
No, sir. No problem, sir. You please continue, sir.
Yes. So we can deploy our models using TensorFlow. So I will in the entire scenario, we'll focus mainly on building a model and checking how a model is performing on mostly on image data sets, and how to do that. So let us start with how to install. So TensorFlow installation, for that you can use either PyCharm, most widely used in the industry, because it can source all models can be all different compilers can be run on at the same time in this. So, but it's only for people who are working in front end, back end. If they want correlation and stuff like that, they go for PyCharm. But most widely used is PyPy or the Spider IDEs. These two are most widely used. And to install TensorFlow, this is what I'm using. So I have already installed Anaconda TensorFlow GPU API. So, or else you can do a pip install also. So let me show you. So to import the first basic command to import all the functionalities of TensorFlow into our code is TensorFlow as TF. So it's taking, so I'm using TensorFlow 2.5 version, but the problem is it was launched only 1 year back. So so the problem is most of the codes that you see online, they are built in like before TensorFlow 2.0. So the problem is it is a highly dependent language on these things, like on the versions of different APIs that TensorFlow uses. So that is the biggest problem. Once you change those, you install TensorFlow 2.5 and it doesn't follow the it's dependencies like NumPy or any other versions. Sometimes it doesn't match and it throws up an error. So that's one thing we have to keep in mind when installing TensorFlow. Now, why people, most of the academic people, they don't, they're switching from TensorFlow to this one. PyTorch from TensorFlow is from Google, PyTorch is from Facebook. Now, why they are switching is those kind of dependencies problems are very less in PyTorch. So that's why they are switching. But TensorFlow is the most widely used industry standard where you can deploy your models. So let us see what exactly the concept behind machine learning. So let me show you. This is a list of numbers from -1 to 4. So let me read them. And if you see the type of input that I'm taking, it's a list. And my output. So this is my input, and this is my output. These are my requirements. So in the, as we have shown in the first figure, inputs and requirements, and the machine will try to learn the rules of the game. So that is what makes it very interesting. That is what the training means, to find a correlation between X and Y. So now here, if you can guess the relationship between X and Y using your biological brain, that would be great actually. So if anybody have something like, if you can identify, if you have identified, you can type in the chat box what is the relationship between X and Y. So that is what humans are good at doing, and we want the same thing to do, because we want the same thing to be done by the machines. And fortunately, humans are good at doing that because they are trained to do that. Because you are trained in linear algebra, where you can give out a mathematical expression which will link between X and Y, which you'll find. Let me show you the relationship. So that is in machine learning terminology, they call it hypothesis. So so y equal to 2x minus 1. So you can just see if you substitute the first element -1, you'll get -3. So all the elements, if you substitute from x, you'll get y, y list. So this is the relationship that we want a system to find. Where it should start, how it finds a relationship. So that is the essence of our talk today. So, and for your information, I'm using Jupyter notebooks. These are most popular and most widely used IDEs for any language, in any language. So you can do it, and so most widely used by even the Amazon AWS and the Google for on their cloud platforms. So they are very powerful tools. So let's build a machine to do this guesswork. So let us build our first neural network. Now this is a dense network. There is no convolution because it's a one-dimensional data. I'm not interested in building a 2D convolution neural network. So I'll just go with. So I'm importing TensorFlow SDF, NumPy for doing the mathematical operations, converting the list, because when you read, we have read that in the form of a list. We want to transform that in the form of an array, because TensorFlow operates on array. So all then they gave the name tensor for one-dimensional tensor for a vector, two-dimensional tensor for a 2D matrix, three-dimensional tensor for a 3D matrix, and so on. because the matrix size sometimes goes to 6 dimensions also in tensor. So 60 matrix, instead of calling that, the Google have invented a new name, and that is called tensor. So all the TensorFlow, all the deep learning models, or the neural networks, or the convolution, the LSTMs, recurrence models, everything is built into, all the functions are built into something called sequential, because the architecture of a deep learning machine, if you see, it's a continuous flow of data from one layer to other. So it's a sequential model. So all the models are preserved, or all the models of their functionality is written into a keyword called sequential. So we'll import sequential, and then we'll import layers, because all that models are initially built into Keras. So if you are using TensorFlow 2.0 and below, the Keras and TensorFlow you have to install separate. So you have to say pip install TensorFlow and pip install Keras separately. Keras works in the backend and TensorFlow in the front end. Now, when you are using that, if you see the models that are built on TensorFlow 2.0 and below, so they will directly write from Keras import sequential. But here 2.5 and above, or 2 and above, both TensorFlow and Keras are merged together. So that's why we have to write TensorFlow.Keras import sequential. And from layers, because everything is, all the convolution or dense, or all the fully connected networks are present in layers. So we'll say dot layers import dense, because the keyword given to fully connected network is dense. Each layer is called dense. So we'll run this, and nothing happens, because it's just importing all the dependencies that are required for running our model. So we'll build a model. So model sequential, that is the function. And in that function, sequential, we are taking dense units, because it's a very small program which takes only one input and one output. I'm building a network with only one neuron. So I'm just saying number of neurons that I want in the dense layer. I'll stick to one, and the input shape of that is again one-dimensional array, because I'm going to read only one input at a time and do the operation. So for each iteration, it reads only one input. So that's why. So these two are most important, and most importantly, these two you have to specify in the dense when you are defining a particular layer, any layer, like convolution also, or any other layer. For the first layer, you have to specify, because rest of the layers, they take input from the previous layer. It is not required to specify the shape and input shape and stuff like that. So here we are specifying. So all that everybody writes like this. So I have also written like this. So I'll run this. So it will take some time to form the model. So it has formed the model, and I'll show you how it looks. So these are the same things which I have discussed. So you have to specify layers inside the sequential, and you can see the model. So dense fully connected layer. So one unit define the number of layers and neurons. We have only one neuron, and you can add different layers to the first layer by saying model.add and df.keras.input, and the shape. We'll see all these things, but I have written to show you how it works. And you can also specify the activation function, because the default activation function is a sigmoid. In this case, I'm not specifying anything, because it's a small program, so it works. Now, if I want to see what is there inside my model, so let me run this, and you can see here, model.summary will give me what are the contents inside the model, how many parameters, trainable parameters, because we have only 2 layers. So we'll have only 2 weights. So that's why the parameters, trainable parameters is only 2. So, and that too, one is weight and the other one is bias. So we have only 2 parameters. So in this, so it's very simple. Because the first layer will only source inputs, the second layer where the actual operation happens. So the bias and the weight for that single neuron. So you'll have only 2 inputs, 2 parameters that are required for training. So we'll have only 2. So that's why the total trainable parameters is 2 in this case. So let me run that and we'll go to the second. So then once we have the model, you have to compile. The regular software stuff where we compile the programs, where it will bundle all the model data, etc., into a single entity to be operated on the different inputs and outputs. So here there are 2 things that we want to define at any point of time in the compile stage. So one is optimizer and the other is loss function. So I'm using a stochastic gradient descent optimizer, which is used to update the weights. In what fashion you have to update the weights, and the loss function. So to calculate the loss between the actual output and the predicted output, we use a simple mean squared error. In this case, there are different loss functions specified for different applications, but we'll focus mainly on mean square error, which is more popular. And there's one more which is very popular, quite popular in for image processing applications that we'll see in the next program. So let me compile this, and then to give input to this, my data should be in the form of arrays. So I'm just converting the entire lists that I have supplied as input into arrays here, np using the np.array, and then to fit the model to the data, and I'm running for 100 iterations. So every time in the first iteration, it will take 1 input, and it will use the random weights. Now, initially the weight and bias will be selected randomly. It will operate on that, and it will find the output. Here, I'll show you what exactly the weights means. The weight here is 2, and the bias is 1. So this we know actually, but the machine doesn't know. So it will select something like 10 or 20 initially, and it will try to calculate the output, and that is called the predicted output. It will check this predicted output with the actual output is -3, and then it generates that error, and that error using mean squared error. And then a mean square, because it has to check for all the inputs. So I cannot do it for 1 input and 1 output. So it will use all the 5 inputs, 6 inputs, and then all the 6 outputs. Collectively, it will calculate the error, whether these 20 that we have selected, the machine selected initially, is giving the correct output or not. So that's why mean square, it will square all the distances or differences, and it will take the average value, and then it will try to find the error, and the error should be minimum, that it should be actually 0. So if it is in most of the cases, in 99.99%, it's never 0. So it will use that error to correct these weight values. So that is what training is all about. So how it corrects these weight values using the error calculated between the predicted value and the actual output. That is what the actual training process is. Let us, for the training process, the most widely used function is dot fit. So you have to just model, because you have compiled all the necessary elements into the model, and then you just fit and give input, output, and number of times it has to run. So if I just run for only 1 iteration, let us see what happens. So it is running for only 1 iteration, and the loss you can see is 1.55. 1 iteration will not give a very good result. So I'll just go for 10. It's running on GPU, that's why it's very fast. And the loss here is 0.65. Now it has reduced the loss. It's constantly doing that. Let us go for 100 and see what happens. Now it's down to 0.70. So 0.7. So the basic most these kind of smaller applications, the loss people talk about is around 10 power minus 2, but most critical applications like where you can go with 10 power minus 1 also. So but it's the standard value of a loss between the predicted values and actual values is 10 power minus 4. We can also select that. You can run for 500 iterations and you can check what will be the loss. You can just see it has shifted from 10 power minus 1 to minus 2, and then you can see minus 4 also. But if you give more epochs, it will run for more, it is trained for more time. Like you increase the training time, obviously your perfection will increase. So that is how the same thing will happen with the machine learning model. So you can see the final error we got is 10 power minus 6. So that's a very good one. But when people will come, this is a very small example that we have selected. If you go with the image recognition task, 10 power minus 1 to 10 power minus 2 will be fine. And what is, so I talked so many words here, so to see that what is the difference between the compiler, optimizer, and the loss function, what they are actually doing. And again, the background is linear algebra that goes on with most of the AI ML models on this planet. So compiler, optimizer, and loss function, what they're doing. So let us see the compiler like bundling different things into a same file. So that is what it is doing. So it collects the information from different places and arrange it in the form of a book or list. So Keras models, the compilation, what they are used. So these are the three main components of any machine learning algorithms of compilation, loss. You have to specify, these are called hyperparameters. So the loss functions, the optimizers, the metrics, the evaluation, and the prediction. So we'll do that. Now, how computers, what actually is happening in the background, that is what is very interesting in this case. So how computers are actually learning, and that process of learning is called training. So at the start, the computer has no idea about the relationship between X and Y. So it will take a random guess, like I have suggested earlier. So it says 10, and it selects the weight vector as 10 and the bias as 10. Now, how good is that 10 value? We have to check. So that is what the measure is. So then it will try to predict the value of Y by substituting different values of X, and that predicted value minus the actual value is called the loss function. So loss function decides the goodness or badness of your guesswork. So that is just like human beings. That is what humans also do. So we validate what our decisions, and the best output of our decision is the error between the actual output and our decision making skills. That is what humans are doing, and the same thing here also. So let us see how it actually happens. Here you can just substitute the values of Y, values of X. Let us say substitute -1, and the predicted value is 0, but the actual value in the list is -3. Now the error is just Y predicted minus the actual. Now y squaring, because you can select y actual minus y predict also. So to remove that,
histogram, correlation, ఈ చిన్న చిన్న పిల్లలు అసలు అంతే గ్రాఫ్స్ చిన్నవి.
yeah, thank you, man. So the relation here, it is that the difference between these two, it can be anyway. So that's why they thought instead of putting a single like a single subtraction, let us square the error. So that is the most widely used metric. And then for all the values of x, we have 6 different values of y. So 6 different errors. Dealing with 6 different errors is again a big task. So instead of that, add all the errors and use that, because 10 is not changing for fixed value of 10. So we'll add all the errors and we'll try to modify the vector 10. So that is the job of loss function. Once we have the loss, this loss should be used to update the weight vector. Now I want to change again. Once this loss function is, this loss is for when the computer guessed it's the weight is 10 and the bias is 10. Now we want to shift this towards my actual output, so that my predicted output will be equal to my actual output. So that is the job that is taken up by the optimizer. So the optimizer, what it will do is it will try to find the differentiation between multiple errors, and it will see in which direction the error is moving. So regularly it will go in the downward direction towards the 0. So that to keep that in that direction, we need to differentiate the output, and with respect to error, differentiate this expression with respect to error, and substitute, find the new values for my weight vector, and just again repeat the same process, and that is the job of optimizer. And it's most of the applications, the optimizer will be moving downwards. That's why it's called descent towards the 0. So it starts with the maximum error and moves towards the bottom of the curve. So that's why it's called gradient descent. And how fast it moves, that is, and more that is the research element in finding a very good optimizer for your application. There most widely used 90% of the applications, they use the stochastic gradient descent, or a new version of stochastic gradient descent that is called Adam optimizer. Adam optimizer is somewhat a thresholded version of SGD, and it also has good performance indices for different applications. And then we'll see whether it has predicted correctly or not for a value of 10. So if you see, let us try something from the list. So we have given -1. Let us try for -1 and see if it is doing correctly or not. So -1, it is giving -2.9. Actually, for the output for -1 is -3. So it is very close, and that is what if you run for like 1,000 iterations, maybe it can give correct result of -3, but -2.99 is pretty much acceptable from a machine learning point of view. So model is working absolutely fine. If I give 0, let us run for 0, and it is almost -1. Now you can do it for any number. Now, so this process is called inferencing. So but we have trained only on 5 samples. Now we can, once the training is complete, you can predict the output for any number, and you can just calculate. It almost gives the correct result. So that is the advantage of machine learning or deep learning. Suppose you are predicting stock market values, you want to predict how the stock will perform in next 5 years, so you can do that by training your model with stock values from now going backwards up to 50 years, and then you can predict the performance of a particular stock in next 5 years or 6 years. And don't expect because it only gets these things based on the input that you are supplying. So most of the time it depends on so many other things also. So entire application, if you see, entire program for this is very small. Now I can show you the weights also. What are the weights on which it has trained? So let me run that, run the model, and oh, it's taking 500 epochs. Now you can see the weights here are 1.99, and the bias here is 0.9. So you can just see the expression that we manually designed is 2x minus 1, and it is the machine is saying it is 1.99 the first weight, and this bias is 0.99. So almost the minus 1 is my bias value. So that is very close. And that is the power of neural network. So if you have any questions, please, you can ask, or you want me to enlighten you on something else. We'll wait for 2 minutes so that you can compile all this and you can ask something. So is my voice audible?
Yes, you're audible.
Yes, yes. So hope you all got the meaning of training and testing the network. So let us dive deep and check how we can use the same thing to build convolution neural networks and on an image data set. So I'm using only the built-in data set in this particular example. That is most popular MNIST data set. It's a handwritten character recognition data set with around 70,000 samples will lead. So how to divide the data sets for training and testing, and how to build a model using convolution neural network. So that is what we are going to see. It's again a basic model. So we'll operate directly on images and see how it works. So what are the requirements? The activation function. The convolution layers basically learns the features, extract the features, and the dense layers is where the actual training of for prediction or for recognition is happening. So the basic layers will be convolution layer, activation function in that layer, the pooling operation in all the layers. So for that, I'm again importing TensorFlow. So this is a built-in data set which is already there in TensorFlow. So I'm using that. It's a fashion MNIST data set. I thought of doing it on the character recognition data set, which was done so many times. So I'm switching to the fashion data set. I'll show you how the data set looks like if I type let us say so this is the data set which I'm using. So it has clothes, trousers, shoes, and stuff like that. Around 10 objects are present in this. So we'll use that data set, which is built into keras.datasets. So TF into TensorFlow dataset. So I'm just importing the data from there, and I'm just the dataset is bundled in such a way that it is divided into for training, images for training, and their labels. And then because it's a supervised learning model where labels are necessary for the images to be classified into different categories. So we have to give the labels also. If when you're doing with unsupervised learning models where the labels are not a necessary component during training process. But here we are doing supervised, and most of the applications that you see are mostly supervised learning models where training labels are or class labels are necessary. So it's already there in that. So let me run this and let us see what is there in data. So it is a link for the TensorFlow model. So and then we'll see what is train images, what is the data that is present in train images. It will show the data set like this because it has so many components. So let me check the shape of so it is for training we'll use 60,000 samples. And if you see the test images, how many test images are there? So 10,000. Totally, the data set consists of 70,000 images of each size, 28 cross 28. So and they're all black and white images or grayscale images. They're not color. So if they're color images, you'll get a cross 3 or one more component, one more vector for defining the RGB planes. So we'll split the data into train images and train labels. If you see train labels, the shape of the matrix, I'll just type it. Labels and check. Okay, I have given the wrong spelling, but anyhow, everywhere I have given the same spelling, so it doesn't matter. Yeah. So 10,000, it's a simple vector. So we can just see the test labels. So 60,000 samples of the data, each of size 28 cross 28, we'll use for training. Rest of them will use for testing. 10,000 will use for testing. And just to show you the shape of the images. Now the problem is once this 28 cross 28, now when it passes through the convolution layers, there should be the images will increase. Why? Because you're doing a convolution operation. So the array vector should take each of the filter outputs also, filtered images also. So we just increase that size of the image, just create an empty vector. So we have to do it when we are giving it to convolution neural network. So the size it accepts. The regular convolution neural networks, they accept size because that extra vector is for saving the filtered output. So just increase the size of your input. So the tried images are reshaped from 28 cross 28 to 28 cross 28 cross 1. So that is the input shape of the first convolution layer. So The point is again, the output of the convolution layer is a 4D vector. So that is the reason why we have to supply the extra one, because here it is missing. So if it is a color image, it's not required. If it is a grayscale image, if it is a matrix of certain size, then you have to augment your matrix by a single empty vector. Now the train images we reshape from is our actual training set is 60,000 cross 28 cross 28, and we are adding the extra dimension because the output to save all the filters that are generated from the convolution layers. So then the same thing we'll do for test images, then we'll run. And this is our model. So let us focus here what exactly our model is. Same as the previous case, but here we are adding convolution layers instead of dense layers. Now the first one, tf.keras.sequential, because all the layers are in sequential model. And then the first layer, there is convolution 1D, convolution 2D, convolution 4D is also available. And recently I've seen 4Ds, but we are here because ours is a simple grayscale image. For any image processing thing, when you are operating on images, convolution 2D will do. So when you're operating in 3D data, so you need X, Y, Z components also, then you can go for 3D convolution. Most of them they do on RGB images or video, they do 3D convolution. So we'll focus here on 2D convolution. So I'll add. So how many filters in first layer? The first component is number of filters, and I'm taking 16 filters. That is your choice based on the application that you are designing. And in my filter dimensions, the patch size or the kernel size of my filter is 3 cross 3, and the activation function is relu. If you don't do it, also it will take a default as sigmoid. Then my input shape, now I am giving my input shape as 28 cross 28 cross 1. So that is my input shape that the first layer should accept from the training samples. So then I'll add the second layer, the max pooling layer of 2 cross 2. The default stride is 2. So if you want to go for more strides, just you have to type comma stride equal to some number 3, 4, whatever you want. But the most of the applications that I have seen in real time also, they use stride 2. That works fine. And then you can add one more convolution layer, and that in that convolution layer we are selecting 32 filters. Again the size I'm keeping constant 3, because 28 cross 28 it comes in, and after the max pooling operation, the size becomes 14 cross 14. So then we are applying on that 14 cross 14 32 filters with again 3 by 3 activations relu. From now on, you need not have to specify the input shape, because the output of the first layer becomes the input to this particular convolution layer. So there is no point in specifying the input shape, because it actually knows what is the input shape that is going to come in. Now next you can add one more max pooling, and you can add one more convolution. Choice is yours, but I'm stopping here because I'm getting a 7 cross 7 vector here. So then this again, it's in the form of a matrix. So I'm transforming that into a vector of size 512 cross 1, 256 cross 1, your choice. Or you can add one more dropout layer, which is not required. So we'll directly flattening it. Flattening in the sense transferring the 2D matrix into a single dimension vector. For you have seen the dense layer, which accepts only vectors as input. So for that, so I'm doing that, and I'm taking only 128 neurons in my dense layer, because all inputs are not required here. So it will filter out randomly and it will select only 128 inputs for my dense layer. So that is, and here activation for my first dense layer, I'm using ReLU. And my second dense layer, my final outputs, I have only 10 classes. So I will stick with 10 dense neurons, each class representing the probability of one class. So I'll select only one neuron per class. No, everybody does that, not only me. So if the number of output classes equal to number of neurons in the output layer. So that is the output layer where the activation function for all the output layers is softmax, or you can specify sigmoid. Sigmoid or softmax both are same, but they use differently. You can specify sigmoid also, softmax. And why? Because the output should be probability. So the activation function transforms the numbers into probabilities of each class. So that is what it is going to do. Right. So once we run the model, you can see the model also, how it is getting connected. So I have to install something for showing you this. So let us skip this. Okay. Right. Yeah. And then optimizer, I'm using here Adam. Like I said, the two most powerful optimizers, stochastic gradient descent or Adam. Both are same. It's a thresholded version of stochastic gradient descent, Adam optimizer, which is performing great for different applications. It was invented 2 years back. Before that, SGD was most popular one. And here I'm using a sparse categorical cross entropy as my loss function. It's a logarithmic loss. It's just a simple information based loss function is based on entropy in information. So it's a very simple one. So why sparse categorical? You can also do categorical cross entropy also. Both are same. And then metrics, I'm measuring the performance of my model, which was really missing in the previous example. I'm measuring the metrics of performance of my algorithm or my model with respect to accuracy, how good, how efficient it will classify different classes based on the test vectors. So let us run this, and then I'm running for only 5 epochs. So let us see what happens if I run this. So it will take, because it's on images, it will take some time. You can just see. And the accuracy is around 80. In the first iteration, it's 82%. And loss is decreasing, and that is a good sign. Now, when you run your program, and you have to check whether it is doing its job properly or not, check for loss function. It has to decrease. If it is not decreasing, then there are some cases where the loss will not decrease, but still you'll get it will give you good accuracies. It happens sometimes in some cases where the model is not designed properly. So if I want to check how the model looks, let me show you. Now this is our model. You can just check here. Now you can ask, sir, we have given 28 cross 28, but it is showing only 26 cross 26. Now we have ignored the borders. So all 4 sides we have ignored the border. So it will the convolution operation will eliminate 2 borders per convolution layer. So the max pooling will divide the 26 to 13, and after convolution I'll have 11, and after that I'll have only 5 because of the max pooling. So my 5 cross 32 will give me 800 samples, flattened samples. Out of 800, I'm selecting only 128 for training. That is where I'm introducing non-linearity. You can also say dropout. You can also increase this number if you want. And in the final dense layer, because I have only 10 outputs, so I'll stick with 10. And first convolution, the trainable parameters are 160 because 16 filters and 10 classes will get 160. And then in the second convolution, the number of filters have increased 16. So 16 into 32 into 10, it will give this number. So number of weight parameters. And here 128 into this parameter will give me. So most of the trainable parameters, 1 lakh 2,528 are there. For a small model like this with 60,000 samples, I have these many parameters. Trainable parameters means weights and biases. So these many weights and biases will be trained. So that is the size of my weight matrix. So this is my model. So you can see if you are working with huge data with big image sizes, the number of parameters will increase exponentially. So that is what happens. Now, once you have trained, you have a trained model. Now, how to evaluate the trained model, that whether it is working perfectly or not. So for that, we'll use model.evaluate. We'll use their test images and my test labels. And then we'll use the model to predict on the test images and see how they are performing. So you can just see here. My loss on the test images is 30%, and my accuracy is 89%. So it's decent because we have trained for only 5 epochs. You can train for more than 5 epochs. Then you can see. And these are my label parameters. That 10 labels that here actually it is showing labels in the form of numbers. So which one it has selected for 0 first input. So this is how we train the model for image classification applications. So please, if you have any questions till now, we can just right. No questions so far. So hope one thing I forgot to tell you this because the pixel range of grayscale image or any images, the coding that Windows or any operating systems on this planet, they use the pixel values from 0 to 255 or 1 to 256. So range, because they are every pixel is coded with a 8-bit vector. That is enough. Actually, it was there from last 25 years or 30 years of evolution of operating systems. So for better training, because it's a lot of multiplications and additions and stuff like that that is going on inside the network. So for better, for faster training times, the idea is to see that whatever values that comes in, they range between 0 and 1. So for that, the basic operation here is to divide, to normalize the training and testing images. So this is the basic operation. For images, it is always divided by 255. So that gives better results. So if you don't do this, nothing will happen, but it will take longer times for training. So let us see if that is the case. I'll just remove these two things. I'll restart my kernel and I'll say run all. Let us see whether it is. I can just check it is running on my GPU. And there is always a transfer between GPU, and each batch goes into GPU, it runs, it trains there, and it comes back. The outputs are saved back into the CPU memory. So that is the operation done by the CUDA toolbox. Now it's taking a little longer, but the accuracy is good. Yeah, the test accuracy has dropped a little bit, but it's okay. The number of parameters and stuff, it will not change much in this point. But it's always good to divide by 255, normalize the input images and output images. So this is the basic data set, but what we want to see is we want to run our convolution neural networks on custom built data sets like your data set. Like you want to use this for your own data set for image classification applications, you can do that. So for that, there are so many data sets available. But I'm considering in this case, I'm downloading the data set from Kaggle. You can also download that horses or humans data set. We have only two classes, either horses. So we have a lot of data sets that are in Kaggle. Again, the company is bought by Google 2 years back. So this is the most widely used data set. It is around 160 MB. So it has both training data set, testing data set, validation data set. Validation is one more term where it's widely used in machine learning, where once in between in between training, whether you want to see that how your model is performing correctly or not, you will have a small test set named as validation set, which will test your model during training process. So that is testing during training process. But actual testing is once the model is trained, then you will test with your test data. And validation is just in between testing, in between training samples. So you want a training process, you will test whether your model is performing properly or not. So we'll work on this horse versus humans data set. So the biggest problem, what I understood, is labeling. So that also can be, that problem is solved using TensorFlow, using image data generator. So for that, this is one thing that comes in very handy for most of the applications where your data set is small and you want to increase the size of your data set for better training. For that, this concept was introduced. So what we'll do, same from TensorFlow.Keras preprocessing.image, import image data generator. So it will do the entire thing for you. The API is written. You need not have to select the images, put it in one folder, and name them, etc. So all that can be done, and you can increase the size of your data set drastically using this. So let me run that. So the train data, we just rescale it by 255 because I'm using images. I'll do the first operation. Then I'll use different methods to access the my directory. So my this train generator, the train data dot flow from directory. So because I'm taking the input from the directory, it's already there in my directory. So I just have to give the path of that. Where is it? Yeah, horse or human. So I have they have only done that. So trained horses, humans, 2 classes. So all these images you can just see. This is the horse image, and if we go back, the humans. These are the human images. So there are quite a number of that in the data set. So let us and the size of my image you can specify. Here I am specifying 300 cross 300. You can specify anything 256 cross 256 or 128 cross 128 based on the way your model is performing. And the class mode, I am writing it as binary because I have only 2 classes. So if you have more than 2 classes, you can just call it categorical, where you'll have more number of like more than 10 classes like in the previous case. But here we have only 2 output classes. I need a binary classifier. So I'm just writing binary. So I'm importing from this data set, which is already there here. So it should not be a problem. So there are 1027 images belonging to 2 classes. So that is what it's saying. Now, all that data is there in images that we have seen. So let us build our model. Now here I'm going for a little bigger model because my size of the resolution of input image is 300 cross 300 cross 3. So I'm going for a little bigger model. Now the first layer has 16 and the 3 by 3. I'm constantly maintaining 3 cross 3 filters. You can change that also. And my input shape is 300 cross 300 cross 3 because it's a color image. So we'll focus on RGB images. Previously it was 1. So here we don't have to add an extra dimension because already 3 is there in the extra dimension. So it will take the 8. So then the max pooling 2 cross 2. And then again I am selecting 32 filters for my second layer. And the activation function is relu. And then I'm selecting 64 in for my third layer, 64 my fourth layer, and fifth layer. I'm selecting more filters. You can also start with 64, 128, 256, 512, 1024 based on your application, based on your computational power, also hardware capability. So how much it can take. And my dense layer, I'm putting 512. Previously, I did for 128 because here the data is more rich in features. So I'm using 512, and the flatten is common because I have to transfer the 2-dimensional features that I get here into 1-dimensional vector for dense layer. So I have only 1 neuron in the output dense layer because I'm just trying to mine is a binary classifier. And as I said, it can be softmax or sigmoid. So to get the probability, so you can also write softmax here it will do the job for us. And let us check the model. So 300 cross 300 will get, will lose 2 pixels, 2 rows of pixels for our inability to process the borders. Then if you want the borders also, it's very simple. You have to write the output of convolution equal to same in the quotation. If you write like that, it will preserve the borders. Now in most of the cases, borders doesn't, 1 pixel doesn't impact the outcome of your experiment. So generally we try to avoid those things, those complications. So then after max pooling, it becomes 149, half of this, and then we lose 2 pixels. For convolution becomes half, 73, then 2 pixels, 35, and finally after max pooling, in the last layer, we'll get 7 cross 7 cross 64, which will come up to 3136. Out of 3136, I'm selecting only 5 call. Randomly, it will select. And then the total number of parameters are 17,04,097. Previously, in the previous example, it was only 1 lakh samples. Now it is 17 lakhs. And previously there was 60,000 training images. But in this case, the number of images are only 1,000. But still, based on that, if you select this kind of network, for that particular input, you'll have 17,000 trainable parameters. In the sense, I'll get 17 lakhs weights and biases. So let us compile. So I'm using, in the previous, I used sparse categorical cross entropy. Here I'm using binary cross entropy because it's only one neuron in the output layer which will have to decide whether it is a human or a horse. That's it. So optimizer, I'm focusing on SGD. You can use whatever you want. Now there is one more idea, like you can save your model. This is the function that we use for fitting the model to the data, model.fit. But there are other functions like model.fit underscore generator, which will take the input from the train generator. This is train generator from this. Now in this, it has already divided into training and testing samples. So you can directly use them instead of you specifying as a programmer what should be the size of training samples and testing sample. We'll give the control to that. But we'll include validation also. So I'm just not running the model. So what is the difference, which I have already talked, the difference between validation and testing. The training data is to teach the network to fit the labels. And validation is to check the network's performance while training on previously unseen data to see how the network is performing during the training process. So that is what validation is all about. So for that, we have to define the validation set. So I'm using the same image data generator to extract the validation content, because I have already validation data I have already stored in my database. So I have test data, I have train data, test data, and validation data. So validation data is previously unseen data, which I'm using to test my model during the training process, not after the training process. That is the only difference. It's like a test, like between during the training process. So let us run that again. I took only 256 images. We don't require a big validation set. So it's a small one is enough. 256 is also a huge number for a data set of size. What do you call around 1,000 images in each class. 256 is a huge number, so you can go with 64 is pretty much good. Now let us incorporate the validation into the model. So generally they write history because once the model is trained, it becomes history. So that's why model.fit. The input is train generator. The number of epochs, we are doing it for 10. The validation data is coming from validation generator. So let us fit that and see what happens. No, just focus while training, just focus on the loss function, whether it is going down or not. That is very important. The validation accuracy should increase along with your. So this is my validation accuracy, and this is my this is my actual accuracy for the training data. So the accuracy here is 0.63, and it is increasing. Again, here it got reduced. It's going down. And you can just see how much GPU space it is occupying. So once it is done, you can just see GPU comes to 0. We are running it for only 10 epochs, but 10 epochs will not do the justice because anyhow, we got an accuracy of 0.85. Sometimes we get maximum 100% accuracy, and still the model will not perform very well. And that process is called overfitting. Like it has learned, the model is overconfident about the training process. That is what it was understood generally. So now once we have trained this, how to test the trained model. So let us do that. Let us predict the images from the test data. So we have test data. So we'll to show the plots, we'll have matplotlib, and to access the directories, import OS. So I'm taking the directory from the test images path, and then I'm extracting the test image. Different test images you can extract. So I'm extracting one image. So let us select an image from the entire test data. I have a test folder, test data. So I'm extracting test data, test image. So let us check the test image. What is the test image? This is the test image that I'm supplying to my data set. The data set is consists of all CG generated images. They are not actual human images, but I'm testing the model with actual human image. So let us see how it will perform. So let us test here. The probability is greater than 0.5. It is a human, or else it is a horse. So the model is trained very well, and it is saying h11 .jpg is human. So this is my input, and it is saying an image that is a human. You can test for different data sets. Will give 8 image. What is that 8 image? So this is one more test. It's also saying is a image. Won't have horses. Yeah, this is a horse. Let us see whether my model can predict it as a horse. Yeah, saying it's a horse. Or we can test with both horse and human. Yeah, here we have both horse and human being. Let us see what my model will tell me. It's saying it's a human. And this is where the model fails. Why it failed? Because it cannot generalize on things like it has both contents, but it has the ability to give only one output. And the maximum why it is saying as human is the human being is the pixel values of human being are because the human being is bright in color. Their values are larger than compared to the horse, which is somewhat dark in color. So that's why it is guessing that it is a human being, not a horse. So let us check some other. Here also, let us check this. Again, it's also saying human. I don't have the 30 number. I think that is the reason why it is saying uh, these images are belonging to human, because the value of pixels, the numbers that are taken by human in this case are larger than the other things. Compared to the background and the horse. So that is the reason why. So you can train for more numbers also, like more epochs also. And you can when you control the size, input size, you have to remodel your design. Let us check what happens if I do it for let us say 200 cross 200, because my model, I think it will not correctly fit the things. Here I have to reshape this input also to 200 cross 200. And well, I should also do the same thing for my validation. So let me restart and clear all my output values. Let us see what happens. Now you can check here. It's only after previously it was good 7 cross 7. Now it is only 4 cross 4. And the number of parameters also reduced. The training is quite faster. And just see the validation is not changing. The accuracy is dropping. It requires more training. Yeah. We have to, the biggest problem is this, we have to control all these things. Again, saying very good, human. Let us test on something else. But the accuracy has dropped to 0.75. Previously, it was 0.8. Again, 200, it is handling very good. Let me still reduce it. to show you where it fails actually. I'll give 128 cross 128. Yeah, here also we have to change. So let me restart. Now, what is this 33 by 33? The entire data set of 1000 and odd will be divided. All 1000 images are not trained at any single point of time. It's not a feasible solution. So what they what the compiler will do is it will accept only a batch size of 32. So if we divide the entire data set, training data set by 32, you'll have 33 sets of data. So it will do it in a batch by batch of size. The default size is 32. So you can go for 16 also. I think default size is 16. Let's see. Yeah, default size is 32. So here the accuracy has dropped drastically and it is again predicting correctly. Here is our model. You can just see here the output is giving only 2 cross 2. So we'll have only two inputs, 2 by 2 matrix in the after the max pooling in the fourth layer. And the number of parameters has dropped from 17 lakhs in the previous first case to only 2 lakh. So that is how we can control different things. If you still reduce, it will become 0. So any questions? That's it for today. Thank you very much. So if you have any questions, you can post in the chat box or you can ask.
Participants, you can unmute yourself and you can ask the questions. Sir will address your queries. Participants, please, you can ask the queries either through chat box or you can unmute yourself. Uh, Kishore sir, seems to be all the participants are very clear. Anyhow, you had given a very good explanation, sir. Mostly, surely there won't be any doubts.
Thank you, madam.
So, on behalf of ECM department, I'd like to thank you for accepting our invitation to be a resource person for yesterday and as well as today. Thank you so much, sir. Thank you for your valuable sharing of your valuable information with us. Thank you so much, sir.
Thank you, madam. Thank you.
Kiran, sir?
Yes, madam.
Yes, sir. Sir, shall we wind up the session?
Yeah, dear participants, we'll be having our session on 2 p.m. today. So kindly join on time. So thank you everyone. So we are going to close this session.
Okay, sir. Thank you, sir.